Lesson 3 from our probability unit. Lesson 3 is about binomial probability distributions. We can check out our lesson objectives here, which say we are going to recognize when an experiment is binomial in nature. So we're going to learn some rules for how we determine if something is binomial or not. And then we're going to learn how to calculate binomial probabilities by applying the binomial probability distribution function, both without a calculator and with our calculator. There are two functions we're going to access today, binom PDF, binom CDF, and you'll have some instructions of how to do so in your notes here, and I'll try to talk you through it as well. So the warm-up, you could actually just pause here and try the warm-up on your own. I'm going to take you through the first example, then I want you to do number 2 and number 3 on your own, and then you can come back and see how you did. So on this first example, it says a fair-sided coin is tossed twice. We are interested in the number of times a head shows up. Complete the table to summarize the results. So you can see on mine, yours is black and white, but on my diagram here, when you toss a heads, you have the red line representing heads, and then you have the blue line representing tails. You have a probability of 1/2 when you flip the coin to get a heads when you flip it, or 1/2 of a chance to get a tails. Now, once I record that, I then have to flip it a second time. So does that impact my second, if I get a heads or tails on the first flip, will that impact my second flip? Hopefully you're saying no, that's going to have no impact at all. It's just a coin. It's the same 2 chances every time. So if I get a heads the first time, what is the chance I'm going to get a heads the second time? It's still 1/2. So the probability of getting a heads first, heads second, that's 1/2 times 1/2, right? So that would be 1/4. We multiply going out our branches of our tree diagram. This is a tree diagram that you see right here on the left. If you toss the heads first, there's a 1/2 chance, and then a tails second, there's a 1/2 chance, so 1/2 times 1/2. Getting a heads first and then a tails would be 1/4. What is the probability of getting a tails first and then a heads? So you're going to toss the tails first, and then you're going to toss heads, so that's also 1/4. And then if you're going to toss tails first and a tails second, notice I'm saying and each time, tails and then another tail, so that's going to be a 1/4 chance. Now, here's our table on the right-hand side. It says complete the table to summarize the results. So we want to have 1 or 0 heads. If we have 0 heads, it means we have double tails. So in order to have double tails, it's 1/2 times 1/2, which is a probability of 1/4. Right? That's to get tails, tails. What is the probability of getting 1 head? Well, we see here there are 2 options. We could have gotten a heads and then a tails, or we could have gotten a tails and then a heads. Notice I said that word or. What does or mean in mathematics? It means addition, right? So the frequency is twice. It happens here 1 time and then here a second time. I'm either getting heads first and then tails, or I'm getting tails first and then heads. So I have 1/2 times 1/2 plus 1/2 times 1/2, or 1/4 twice, hence the frequency here, right? So my probability of getting 1 head when I flip a coin twice is 1/2 of a probability, or I could have kept that as 2/4. What is the probability of getting 2 heads? Well, there's only one option here. 1/2 chance to get a heads on the first flip, 1/2 chance to get a heads on the second flip. So there's only one option, so that was 1/2 times 1/2, or 1/4. Now if you're looking at this right here, this is representing all of the probabilities. So if these are the only 3 outcomes that we have, we either can get 0 heads, 1 head, or 2 heads, then my 3 probabilities need to have a sum of what? So hopefully you're saying they need to have a sum of 1, because these are the 3 possible outcomes, and 1/4 plus 2/4 plus 1/4. So all those probabilities need to add up to 1 whole. All right, try the rest on your own, and then you can come back and compare with me. Okay, I'm assuming you went ahead and did number 2, and that was fine. Now I just did number 3, and what you should have noticed is If we want to get 0 heads, there's one way of doing that. That's down here, just getting all tails. That was a 1/16 possibility. In order to get 1 head, well, we had 1, 2, 3, 4 options. So there were 4 times that we could have gotten 1 head. So that's 4/16. In order to get 2 heads, well, we had 1, 2, 3, 4, 5, 6, all my circled greens there. So there are 6 ways to get 2 heads, 4 ways to get 3 heads, and 1 way to get all 4 heads if you flipped your coin. So 1, 4, 6, 4, 1. We flipped the coin 4 times. Interesting. And we got the numbers 1, 4, 6, 4, 1. What does that look like? Hopefully you recognize that that is indeed the numbers of Pascal's triangle. So Pascal's triangle is coming back, and it will be useful in these binomial probability problems. All right, let's move on and try the next one. All right, moving on to another example. Let's see if this follows the same theme. It says, suppose the spinner has 3 blue sections and 1 white section. Consider twirling the spinner 3 times. We are interested in the number of times the spinner lands on blue. So we have 3 sections of blue, 1 section of white. They're all evenly distributed. So there's a 3/4 chance. The probability that it's going to land on a blue is 3/4. The probability that it's going to land on a white then is 1/4. All right, so letter A, it says find the probability that you're going to get 0 blue. In order to get 0 blue, we need to get white, white, white. So there's one way of getting white, white, white. That's 1/4 times 1/4 times 1/4. So that's just 1 times 1/4 to the 3rd power. We're not going to calculate the probabilities. We're just going to leave them like this for now and see what our pattern is. So what is the probability that we spin and get 1 blue? So we've already laid it out here for you. You can see we can either spin the first time and get a blue, spin the second time and get a white, spin the third time and get a white. So it's blue, white, white. So that's 3/4 times 1/4 times 1/4. Or we can spin and get a white, and then we can get a blue, and then we can get a white. So that's 1/4 times 3/4 times 1/4. Same thing, 1/4, 3/4, 1/4. Or we can spin and get a white, and then a blue, which is 1/4 times 1/4 times 3/4. So 1/4 times 1/4 times 3/4. So we have 3 ways of getting 1 blue. So it's 3 times 3/4 to the 1st power and 1/4 to the 2nd power. All right, how about 2 blue? So we can get blue, blue, white, or blue, white, blue, or white, blue, blue. So we can get blue, blue, white. So that's 3/4 squared times 1/4. Or we can get blue, white, blue. Again, we have 3/4 times 1/4, so it's 3/4 squared times 1/4. Or we can get white, blue, blue, which is 1/4 times 3/4 squared. So we're 3 ways that we could have gotten 1 or 2 blues and 1 white. And finally, our last one is what is the probability of getting 3 blue? Well, 3 blue is right here, blue, blue, blue. So it's 3/4 to the 3rd power, and there's only one way to get that. So once again, what do you notice? Hopefully you're saying this is Pascal's triangle. It's 1, 3, 3, 1. We have something to the 3rd power. This 1/4 decreases to the 2nd power, decreases to the 1st power. It's 0. 3/4 to the 0 power up here, right? It's 3/4 to the 0 power, therefore we didn't write it. 3/4 to the 1 power, 3/4 to the 2nd power, 3/4 to the 3rd power. So it is Pascal's triangle. So our binomial probabilities are related to Pascal's triangle. So let's still look and see how. If you didn't read through the notes before you got to this binomial probability distribution piece, then I would pause and just kind of go back and look through that summary of how it's related to Pascal's triangle. And then you can have a little pause here and read through these 2 paragraphs. So your binomial probability distribution, the really important part in order to know if something is a binomial experiment is you must have independent trials. So you must have an independent trial where there's two possible outcomes. We call one of the outcomes your success, the probability that the event actually occurs, and one of them is your failure, the probability that the event does not occur. So if you have success and failure, only those two outcomes, then we call it a binomial, hence the word bi there, binomial experiment. Trials are independent. This is really important. That means this probability of success won't change from one trial to the next. So when you flip a coin, it doesn't matter if you got heads or tails on the very first try. When you flip it a second time, you still have the same probability of flipping it heads, 1/2. If you spin a spinner, it doesn't matter what you spun the first time around, you spin it, you have the exact same chances the second time. If you roll dice, right, rolling and trying to get a sum of something, it doesn't matter how many times each time you pick up the dice, you have the exact same chances of rolling a 7 or rolling a 6 or rolling a whatever that possible outcome is that you're looking at. So those trials are then independent. So it's really important that your trials are independent of one another. So remember this formula, it's on your formula sheet. This formula is going to be used for your binomial experiment. N is the number of trials. Did you pick that up in your former examples, right? If you were going to spin the spinner 3 times, then it was to the 3rd power. So N is the number of trials. X is the number of successful outcomes that you have, right? Usually we put that as an R. So we could have said that's an R in our formula. R is the number of successful outcomes to the power of N minus R. That's your probability of failure is your Q, right? So you take your N minus your probability of success, the number of successful outcomes. Anyway, what you know about these two exponents is that they add up to give you the sum of N. Now, whatever these values are, probability of flipping a coin, getting a heads is 1/2. That's your probability of getting a heads is 1/2. Probability of getting a tails is also 1/2. These two outcomes, this would be your success. If I said what is the probability of getting a heads, that would be my success. So flipping of tails would be my failure. So your heads and your success and failure needs to add up to one whole. So before when we were doing the probability of spinning a spinner and getting a blue or a white, I think it was. Probability of spinning and getting a blue was 3/4. Probability of spinning a white was getting 1/4. Notice these probabilities, right? We can say what's the probability of getting a blue? That's our success. Then the failure is not blue. And not blue is the same as getting a white. So your success and failure need to add up to give you 1 for your binomial experiment. So let's practice here and see which one of the following are binomial experiments. So in order for it to be binomial, you need to have either success or failure. So you have 2 possible outcomes. One you would call success, one you would call failure. And the other thing is the events need to be independent of one another. So you need to have probability of success, you need to have probability of failure, only 2 outcomes, and they need to be independent of one another. So you might want to pause and try it on your own. Maybe circle the ones that you think are binomial experiments and cross off the ones that you don't think are binomial experiments. So go ahead and pause and try this on your own. Okay, so hopefully you said just A and D were your examples of binomial experiments. Why? Look at A and B, what's the difference? So for A, it says selecting 5 cards with replacement. The only way, and then recording to see how many clubs appear. So the only way that selecting cards can be independent of one another is if you actually replace them. So you would select a card, look at it, record what you had, put it back. Select a card, look at it, record what you had, put it back. So there would be 13 out of 52 chances of getting a clubs every single time. So that would be an independent event, and you would have success or failure, probability of getting clubs or not clubs. Letter B says selecting 5 cards without replacement. Well, you would have 13 out of 52 chances for your first card, but then it would reduce. If you selected a club, you'd only have 12 left out of 51 cards. So that is depends on what you picked in your first trial. So if you don't replace it, we no longer have independence. So therefore, this is not an example of a binomial experiment. We have two outcomes, clubs or not clubs, but they are not independent of one another. Part C, asking 100 voters which of the three major political parties they supported. Well, here's the key here, 3. 3 means it's not binomial. You could have Democrat, Republican, and Independent. So as soon as you can't categorize, it's just, if you said Democrat or not Democrat, or Republican or not Republican, then you can make it binomial, but otherwise it's going to fail because it has 3 possible outcomes, so it's not binomial. Selecting a committee of 3 seniors and 2 juniors to organize prom. So would that be success or failure? Would that be independent, or not independent? So does it matter which 3 juniors I select? Or 3 seniors, and 2 juniors? Well, it's going to depend. So this is not independent again, because it's going to depend on which person you select, how many people are left over. So whoever you choose the first time is going to impact what you have left over. So you're going to have some kind of not independent relationship. So it's going to depend on what happened, whoever you chose the first time. All right, let's look at example 3. It says each of the following experiments represents a binomial because there are only 2 outcomes for each trial. You have success and you have failure. Use the binomial to calculate each probability. So a coin is tossed 6 times. What is the probability that it shows up heads twice? So my probability of heads is 1/2. This is my success. This is my failure. If it's not heads, then you fail. So what is the probability of not getting heads? Well, that's 1/2 as well. So we have 6 times that we are tossing it. That means n equals 6, right? My probability of success is 1/2. My probability of failure is 1/2. We want heads to show up twice. That means what? Well, that means my R is equal to 2. So I'm just going to do 6C2. That's my coefficient in Pascal's triangle. So I can either go down and do 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and keep going until I get to this row with the 6 in it. 1, 6, 15, 20, 15, 6, 1. So now I'm talking about these are my coefficients. And I want 2 heads, so I could figure it out this way, but that's going to be too complicated. So instead I'm just going to use that formula, right, which is NCR, and then you're going to have your probability of success or failure. You have to decide to what power, and then your probability of failure to the other power. So instead of using that formula, I'm just going to try to point out what I'm talking about here. My probability of getting a heads is 1/2. I want heads to show up twice. That means I have to take that to the second power. My failure is 1/2. Now what do I know about these exponents for this particular example? When I have this formula, I know that I have to take my n and subtract my r, or these two have to add up to the n, which is 6. So I'm going to have 6 choose 2, 1/2 to the second power, and then 1/2 to the fourth power. That's a little confusing because the probability of flipping and getting a heads versus a tails is the same probability, so it's hard maybe to decipher what we're doing here. Let's look at letter B. It says a die is rolled 3 times. Find the probability of rolling exactly 1/4. So the probability of success is rolling a 4. Well, that's a 1/6 chance. So I can do 4 or not 4. So the probability of failure is not 4. Well, there are 5 numbers on a die that are not 4s. So my probability of failure is not 4, is 5/6. So a die is rolled 3 times. This tells us what n represents. So I'm rolling a die 3 times. I want to get exactly 1/4. So it's 3, choose 1. If my success is 1/6, this is the probability of getting 4. I want to get that 1 time. So my 1 goes here. Therefore, my failure has to have an exponent of what? Well, remember these exponents need to add up to your n. So this is going to be 2. And you can calculate these values. I haven't calculated them, right? I'm just focusing on the setup. You can go back and do the calculation on your own. Okay, letter C, a spinner which lands on red 60% of the time and on blue 40% of the time is spun 5 times. So if it's spun 5 times, hopefully you're saying to yourself that's n is equal to 5. What is the probability that turns up red twice? So red is 60%. You could put 0.6, or you could put 3/5, or you could put 6/10. It's up to you. Therefore, the failure is 1 minus that, or 0.4, or 2/5. Up to you. I'm spinning the spinner 5 times. It's 5 choose. How many reds do I want to get? I want to get red twice, so it's 5 choose 2. So now what do? I have my red, which is 0.6 or 3/5. Actually, I'm going to put in 3/5. And I want that to happen twice. So that's 3/5 to the second power. Therefore, my failure is going to be to what exponent? Well, again, these two numbers need to add up to give you n. So if your success has to happen twice, then your failure is going to happen 3 times because we're spinning the spinner 5 times. So then you would calculate this. All right, try the last one on your own. Pause and try the last one. Okay, this one was a little bit trickier. So did you get this? There are 30 black blocks, 10 white blocks. So you had to see that there were 40 blocks in there altogether. So if you draw a block, what is the probability that it's going to be white? Well, there's 10 out of the 40, so it's a 1/4 chance. What is the probability that it's not going to be white or it's going to be black? It's a 3/4 chance. So that's how I'm getting these numbers here. So be careful. That's the first thing you need to make sure you did correctly. It says we're going to take a block out, record it, and replace it. So replacement is essential. That's what makes these independent events and allows us to use the binomial probability theorem. So then we see that we're going to make this happen 4 times. So n is equal to 4. What is the probability that all the blocks are white? So that means 4 of them, you're choosing all 4, and they're all going to be white. So it's only 1/4 to the 4th power. So 4 choose 4 is the same as just the number 1, so it's just 1/4 to the 4th power. All right, let's try the next one. Again, you can pause at any time and try this on your own and then come back and check your work. So in a dice game, a player's turn consists of rolling 4 fair 6-sided dice. Calculate the probability that a player's roll would have exactly 3 6s. So first of all, ask yourself, are these events independent? So if I roll those 4 die, does what I roll on one of them impact the other? Hopefully you're saying the answer to that is no. Therefore, this is an independent event. Whatever you roll on one die does not matter and won't impact how you roll on the other one. So the other thing you want to ask yourself to make sure it's binomial is there a probability of success and failure? Well, here my success would be to roll a 6. So can I do probability of rolling a 6? That would be 1/6, and then probability of not rolling a 6. So can I separate it into success and failure? Yes, I can. So if my probability of rolling a 6 is 1/6, then my probability of not rolling a 6 is 5/6. I have 4 die, so my n is equal to 4. Rolling 4 at the same time is like rolling die, recording the number, picking up that same die, rolling it again, recording that number. So you do that 4 times. So same. So my n is equal to 4. I have 4 die I'm going to roll. I want to get exactly 3 6s. So this is my r, essentially, right? And the probability of rolling a 6 is 1/6. So that's to my 3rd power. And the probability of failure or not rolling a 6 is 5/6. And once again, this number n, these 2 exponents need to add up to give me that value, so it's going to be to the 1st power. So then I would calculate this, get your answer, 4 factorial over 3 factorial, 1 factorial. You should be able to do this on your own. 1 over 6 times 6 times 6 times 5 over 6. Do some canceling, see what you get. Okay, the next question is slightly more intriguing, a little more complicated. It says, what is the probability of rolling at least 1/6? So at least 1/6 means 1/6 or more than that. So that means the probability of rolling 1/6. How do I write that? 1/6. Or the probability of rolling 2 6s, or the probability of rolling 3 6s, or the probability of rolling 4 6s, because we only roll the 4 die. So do I want to do all of these things and add them together? No. The only value that is not here, we can have 1 6, 2 6, 3 6s, or 4 6s. So the only probability that is not here is the probability of rolling 0 6s. So if all of my probabilities of rolling 0 6s, 1 6, 2 6, 3 6s, or 4 6s, they should all add up to 1. So I'm going to calculate its complement, we call it. So this is the complement. So 1 minus the probability of rolling 0 6s is going to equal the same answer as calculating the probability of rolling 1 6, or the probability of rolling 2 6s, or 3 6s, or 4 6s. Except this way of doing it is going to be a lot faster, right? So if I'm thinking of all my possible outcomes, we could roll 1, 2, 3, 4, or 0 6s. The only thing that's not in at least 1 6 is 0, so I'm going to do 1 minus the probability of rolling no 6s. That's 1 minus, well, no 6s means there's a 5/6 chance 4 times, right? My probability of not rolling a 6 is 5/6. I'm going to do that 4 times in a row, so it's 5/6 times 5/6 times 5/6 times 5/6. So then you could calculate your answer. Okay, now we're going to talk about how to use your calculator, because we don't always make you calculate binomial probabilities by hand. We also will ask some of these binomial probability questions on the calculator portion of your assessments. So I'm not going to show you my calculator, but hopefully these screenshots will be good enough. You're going to use your menu button. You're going to look for probability. You're going to look for distributions. You can also find distributions under statistics. It's going to be the same. So probability or statistics, then go to distributions. And what we're going to talk about using today is either binomial PDF or binomial CDF. So PDF is one singular probability that we're going to calculate, like whatever the outcome, specific outcome happening just the one time. And then C is your cumulative. So you want to do the words at least or at most. That's what we use when we are doing cumulative or between. So otherwise it's just one singular time that it's happening. And then showing work on your paper, you'll have to write this down on your paper, and that's how you're going to show your work. So you'll have to write this first down. This will be a method mark, and then this will be an answer mark. This will be your method mark. This will be your answer mark. So let's try it. You should definitely be plugging these into your calculator, making sure you're getting them to work. So example 5, it says the probability that a college student will graduate is 0.35. Determine the probability that out of 10 students, so 10 is our N, and the fact that they will graduate is our success. So probability of success means probability of graduating. So probability of failure is then 0.65. Okay, we really don't need the failure when we're using our calculator. You can see up here, we just need to know the number of trials, the probability of success, and then which particular value we're looking for. If it's CDF, if it's cumulative, we need the number of trials, the probability of success, and then we have our lower bound and upper bound, and we'll talk about that when we do these examples down below. So part A says, what is the probability that 3 will graduate out of these 10 students, right? So you might be thinking, okay, let's do it in our binomial world. So we have 10 students, we want 3 to graduate, so that would be 0.35 to the 3rd power, and then 0.65 to the 7th power, because again, these two exponents need to add up to 10. This is my probability of success. I want 3 to graduate, that's success. This is my probability of failure. So the other 7 students out of the 10 are going to fail. Now you can punch all of that into your calculator, which would take a long time. So instead, we are going to use binom PDF. So go to your menu, go to probability, go to distributions, and choose binom PDF. I know on my calculator it's not letter D, I think it's letter A, but I'm not sure. So choose your binom PDF. How many trials do we have? We have 10. What is my probability of success? It's 0.35. Oops, I didn't mean to close that parentheses there. And how many people, which particular probability am I looking at? I'm looking at for 3, because I want 3 successfully to graduate. So you would write this down on your paper to show your work. You plug that into your calculator, and do you get 0.25222? Again, 3 decimal places, or you can keep a few more, but that should be your answer. Okay, now look at our very next question. It says, what is the probability out of our 10 students that at least one will graduate? So here we have this word, at least. So at least means we're going to have a cumulative, so we're going to have our binom CDF. And you probably don't want to do this by hand. Instead, now we're going to use binom CDF. There are 10 trials, right? So my number of trials is 10. My probability of success is 0.35. If I want at least one to graduate, what does that mean? That means X is greater than or equal to 1. Okay, not quite, because we only have 10 students, so it's just caught in between 1 and 10. But the word at least is inclusive, so you are including that 1. So you're going 10.35, 1 to 10. You have a CDF there because it's cumulative from 1 to 10, so you should get 0.98653, blah, blah, blah. So what is the probability that at least one of them will graduate? That means one will graduate, or 2, or 3, or 4, or 5, or 6, or 7, or 8, or 9, or 10. So that's a huge, because the only thing we've eliminated is the probability that 0 students will graduate. So we also could have done 1 minus the probability of 0 students graduating. But that would even take longer. So with your calculator, this is super short. Okay, how about our next question? It says, what is the probability that at most 5 will graduate? At most means we're going to do less than or equal to 5. Except that's not actually true, because we can't have negative people. So we're actually finding out the students caught between 0 and 5. And the word at most is inclusive. So once again, it is a cumulative, so we're going to do binom CDF. We have 10 possible people. Probability of success is 0.35, right? Our lower bound this time is 0, and our upper bound is 5. So you should plug that in, binom CDF, and you are going to get 0.90506, etc. All right, that was just a little snapshot of how to use your calculator. Here's another way, another question. You can also use your calculator to try to find your answer here. It says a shipment of computers come, and we know that 5 out of the 25 computers are faulty. We select 10 of these computers to use in the math lab. What is the probability that 2 of these computers are faulty? So the reason we suddenly threw this problem in here is because we have faulty computers. There's 20 that are faulty. And there's 5 that are faulty, and there's 25 that are not faulty out of the 25 computers we have. You immediately might be thinking, okay, this is probability of success. This is probability of failure. I guess the way this is actually faulty seems like that should be failure, but that's okay. It's our success in this case. The problem is what? So we cannot actually use the binomial theorem here. So this is a no. We cannot use the binomial theorem. Why? Because this example is not independent. If I take one computer out of my stack of 25 computers, right, I had 25, so maybe the first one I chose is faulty. So 5 out of the 25 are faulty. Now, what about my second one? And I take a second computer. Well, I only have 24 computers left, and there's only 4 faulty ones. So this is a dependent event. So we cannot use the binomial theorem. Therefore, what do we do instead? Well, we treat it like those questions that say you have a 5-card hand and you want to have all 5 hearts, or you want to have 3 hearts and 2 diamonds. So we have 2 computers that we want to be faulty, but we're selecting 10. Well, 2 of them are faulty, so 5 are faulty altogether. We're choosing 2 from the 5 faulty ones. Does the order in which I select them matter? No. There are 20 computers that are not faulty, and of the 10, 8 of those are not going to be faulty. So we have 2 faulty, 8 not faulty out of 5 that are faulty, and 20. And then there's 25 computers altogether, and we're selecting 10 of them. So you should have gotten 0.3854. You would plug these into your calculator, right? You can use the combination and try that. And then part B, at most 1 computer is faulty. So at the most, that means you're going to have 0 faulty, or you're going to have 1 faulty. So at most means 1 or less than that. But you can't go below 0 because you can't have negative computers. So try to figure out what this would be. I'm just going to tell you the answer. When you plug it into your calculator, you should get 0.3134. After you do something like we did in part A, when you put it into your calculator, do you get 0.3134? If you do, you got it. Good job. If not, check the answer key or ask your teacher. Bye.